Every day, we check the time on our phones, watches, and computers. But have you ever paused to consider what time really is and how we measure it? The story of timekeeping is a fascinating journey that stretches back thousands of years, from ancient stone circles to the atomic clocks of today. In the beginning, the oldest clocks weren't machines at all. They were the sun, moon, and stars. Ancient civilizations, like those who built Stonehenge, observed how sunlight aligned with specific stones during solstices. These celestial alignments mark the changing seasons, crucial for farming and rituals. This is celestial mechanics at work, the predictable motion of planets and stars, governed by Newton's laws and later Einstein's relativity. Even before we had equations, we had patterns, and timekeeping began with the art of astronomy. Fast forward to the 17th century, and we meet Galileo. He noticed that a swinging lamp in church took the same amount of time to complete each swing, revealing the principle of simple harmonic motion. This principle states that a restoring force acts to bring a system back to equilibrium. Inspired by this, Christian Huygens built the first pendulum clock, which gave us precision mechanical clocks accurate to within seconds per day. This wasn't just about being on time, it was about survival at sea. Sailors needed to determine their longitude by comparing local time with the time at a fixed location, like Greenwich. But clocks on ships would swing, drift, and fail. Enter John Harrison and his marine chronometer, a masterpiece of engineering that used principles of physics like inertia and temperature compensation to stay accurate on moving ships. This innovation made global exploration possible. Then, in the 20th century, clocks took a giant leap forward with quartz technology. Quartz crystals vibrate at precise frequencies when an electric field is applied, thanks to the piezoelectric effect. This steady tick made quartz clocks cheap, reliable, and accurate to fractions of a second per day. Here, solid-state physics met electromagnetism, making timekeeping truly portable. But the most precise clocks don't swing or vibrate. They rely on quantum physics. Atomic clocks measure time by counting the frequency of microwaves needed to make electrons in a cesium-133 atom jump between energy levels. That frequency, exactly 9,192 on 631,770 Hz. This defines the second. Atomic clocks are so accurate that they only lose 1 second every 100 million years. Yet, timekeeping isn't just about precision, it's about perspective. Einstein taught us that time is relative. In special relativity, moving clocks tick slower. In general relativity, clocks near massive objects tick more slowly due to gravitational time dilation. These effects are real and measurable. GPS satellites must correct for both to maintain accurate positioning on Earth. Time isn't fixed, it bends and stretches. Physics has shown us that time flows differently depending on where you are. Atomic clocks were just the beginning. Now, physicists are developing optical lattice clocks, which use lasers to trap atoms and measure vibrations at even higher frequencies than cesium. These clocks are so precise, they could detect subtle changes in Earth's gravity, monitor tectonic shifts, or even search for dark matter by observing slight changes in atomic frequencies. This isn't science fiction, it's quantum metrology, the cutting edge of time. From the motion of stars to the oscillation of atoms, physics defines every tick of every clock. Time is more than just something we track. It's a window into the structure of reality. With every new advance in physics, we don't just measure time more precisely, we deepen our understanding of what time truly is. So, the next time you check the clock, remember, behind every second lies centuries of science.